Hello students, welcome to EPG Pathshala. I am Dr. Imtiaz Hassan from Jamia Millia Islamia, a central university. Today we are going to talk on module IR spectroscopy, in which we discuss about the vibrational spectroscopy, types of vibration, homonuclear atoms, heteronuclear atoms with dipole moments, heteroatoms with change in dipole moment under the paper, techniques used in molecular biophysics part 2. After studying this module, students will be able to understand the basic principle of IR spectroscopy. Then we discuss about the components of IR instruments, IR spectrometer. Then we talk about the sample handling techniques, theory of molecular vibrations, the IR spectrum, and application of IR spectroscopy. So let's start with the IR spectroscopy. IR spectroscopy is applied to the qualitative and quantitative determination of molecular species of all types, like chemicals, organic chemicals, inorganic chemicals, biomolecules, and all these things. IR spectroscopy is the measurement of wavelength and intensity of absorption of mid-IR light by the sample. Mid-IR is energetic enough to excite the molecular vibration to higher energy level. The wavelength of IR absorption band is characteristic of a specific type of chemical bonds, which is actually used for the identification of different types of molecules. The most widely used region in the mid-IR that it extends about 670 to 4000 per centimeter. The near IR region from 4000 to 14,000 per centimeter also finds considerable use for the routine quantitative determination. The far IR region has been used for the determination of a structure of inorganic and metallic organic species. We discuss the different types of electromagnetic radiation ranges, and you know that the light are containing different types of electromagnetic radiation, and it having the different wavelength and different frequency, different all the parameters are the different. So generally the radio wave, it having the frequency in 10 to the power 4 to 10 to the power 12 hertz, and its wavelength ranges from 3 into 10 to the power 4 to 3 into 10 to the power minus 4 meter. And the infrared, it is having the frequency around 10 to the power 11 to 10 to the power 14, in the range of 10 to the power 11 to 10 to the power 14, and its wavelength is ranging from 10 to the power minus 3 to 10 to the power minus 7. The visible light having its very high frequency in the range of 3.8 into 10 to the power 14 to 7.5 into 10 to the power 14, and its wavelength is ranges from 8 into 10 to the power minus 7 to 4 into 10 to the power minus 7. However, the UV is a high energetic wave, and it having its frequency is from 7.5 into 10 to the power minus 10 to the power 14 to 3 into 10 to the power 17. However, its wavelength ranges from 4 into 10 to the power minus 7 to 4 into 10 to the power minus 9 meter. And X-ray is a more energetic. Its frequency is 3 in the range of 10 to the power 17 to 10 to the power 19, and its wavelength ranges from 10 to the power minus 9 to 10 to the power minus 11. And most energetic are the gamma rays. Its frequency is 3 into 10 to the power 19, and its wavelength ranges from 10 to the power is less than 10 to the power minus 11. We discuss about the infrared radiation. The infrared radiation have the wavelength of 2.5 to 17 micrometer, and its frequency is around 4000 to 600 per centimeter. These frequencies match the frequencies of covalent bond stretching and bending vibrations. Infrared spectroscopy can be used to find out about the covalent bonds in a molecule, and that's what it is used to tell you the information about what type of bond present in a molecule, and based on that you can gain some insight into the structure information of the molecules under investigation. Now we talk about the theory of infrared absorption spectroscopy. For a molecule to absorb IR, the vibration or rotation within the molecule must cause a net change in the dipole moment of the molecule. By the alternating electric field of the radiation interacts with the fluctuations in the dipole moment of the molecule, and if the frequency of radiation matches the vibrational frequency of the molecule, then radiation will be absorbed and causing a change in amplitude of the molecular vibration. The electromagnetic radiation can interact with matter in two ways. One is the collision, when particle to particle and energy is lost as heat in the moment. The another way of interaction is the coupling. In this case, the wave property of the radiation matches the wave property of the particle and coupled to the next higher quantum mechanical energy level. In IR spectroscopic process, the quantum mechanical energy level observed in IR spectroscopy are those of molecular vibration. We perceive this vibration as a heat. When we say a covalent bond between the two atoms is of a certain length, we are citing an average because the bond behaves as if it were vibrating a spring connecting the two atoms together. Like you can see here that, for example, diatomic atom, this model is easily to visualize that how the stretching between the two molecules occurs and induces the dipole-like configuration. Here we try to show you that there are two types of bond vibration. One is the stretching and one is the bending. You can see a stretching vibration or oscillation along the line of plane. And they are again two types, either symmetric when the both are in this having the same frequency of oscillation. However, it is asymmetric. You can see here in the animation that the having the different mode of vibration. The bending is again are of many types, like they are in plane or it is out of the plane. When it is in the plane, you can see here it is the scissoring vibration or it is the rocking vibration, you can see here in the animation, and in the out of plane it is either twisting or wagging. So before knowing the IR spectroscopy, you must know these kind of vibrations are present in the molecule and which can be mainly detected by the IR radiation using IR spectrometer. Here I try to show you that the covalent bond oscillates due to the oscillation of dipole of the molecule. A varying electromagnetic field is produced. You can see here the variation of diatomic molecule approximate an oscillating spring. The greater the dipole moment changes through the vibration, the more intense electromagnetic field that is generated. So this animation clearly tells you that what kind of oscillation occurs along with covalent bond. Here we discuss that when a wave of infrared light encounters this oscillating electromagnetic field generated by oscillating dipole of the same frequency, the two wave couples and IR light is absorbed. The coupled wave now vibrates with twice of the amplitude. You can see here that beam from the IR spectrometer, and when they are coupled together, the oscillating wave form bond vibration, and that's amplitude is twice of that, which is perceived in the form of IR signal. Now we talk about the components of IR instruments. Dispersive instrument, which has a monochromator to be used in the mid IR region for the spectral scanning and quantitative analysis. In the case of Fourier transform IR system, widely applied and quite popular in the far IR and mid IR spectrometry. The non-dispersive instruments used to filter for the wavelength selection for an IR absorbing gas in the detection and system for the analysis of gas at a specific wavelength. And the modern dispersive IR spectrometer are invariably double beam instrument but may allow single beam operation via the front panel switch. As the source light generates light across the spectrum of interest, a monochromator which separates the source radiation into the different wavelength as the required by the sample Then oscillate selects the collection of wavelength that shines through a sample at a given time. In double beam operation, the beam supplier separates the incident beam into two halves, goes to sample and half to the reference. The sample absorbs light according to its chemical properties, and thus the detector collects the radiation that passes through the sample, and a double beam operation compares the energy that's going through the reference. So after the detecting the reference, you can get the actual information about the IR spectrum, and the detector puts out the electrical signal which is normally sent directly to the analog recorder, and by that you will getting the information about the IR spectrum of any molecule under the investigation. Now we talk about the sample handling. Sample handling is a very essential component of the IR spectroscopy. If you are unable to handle sample properly, there are many chances of occurrence error are there. That's what you have to aware with the sample handling. Sample handling is frequently and most difficult and time consuming part of the IR spectrometric analysis, especially for the gases. The spectrum of low boiling liquid or gas can be obtained by permitting the sample to expand an evacuated cylinder cell equipped with the suitable window. But for the solution, a convenient way for obtaining IR spectra is on the solution prepared to contain known concentration of the sample. Solvent should be transparent and over significant region of the IR, so it should not absorb the IR radiation. And for the solvent, no single solvent is transparent throughout the entire mid-IR region. Water and alcohol are the seldom implied because they absorb strongly attack alkali metal halides. For the solid, most of the organic compound exhibit numerous absorption peak throughout the mid-IR region, and finding a solvent that does not have overlapping peak as it often impossible. As a consequence, spectra are often obtained on dispersion of the solid in a liquid or a solid matrix. The other way to make the sample is by pelleting. One of the most popular technique for the handling solid samples has been used KBR pelleting. A milligram or less or finely ground sample intimately mixed with about 100 milligram of the dried potassium bromide powder. The mixture is then passed in a die at 10,000 to 15,000 pounds per square inch to yield a transparent disc. Then the other way is to form the moles IR spectra of the solid that are not soluble in an IR transparent solvent or are not conveniently pelleted in KBR are often obtained by dispersing the analyte in a mineral oils or fluorinated hydrocarbon moles. Moles are formed by grinding 2 to 5 milligram of fine powdered sample in the presence of 1 or 2 drops of heavy hydrocarbon oil. Now we discuss about the molecular spectra. There are 3 basic types of optical spectra that we can observe for a molecule. First is the electronic or vibronic spectra. It is the UV visible or near IR region, and transition between a specific vibrational and rotational level of one electronic state and a vibrational and rotational level of another electronic state. The second is the vibrational or vibrational rotational spectra in the IR region, and the transition from one rotational level of one vibration level to the rotational level of another vibrational level in the same electronic state. The rotational vibration in the third is the rotational spectra in the microwave region, and it is the actually transition between the rotational level and the same vibrational level of the same electronic state. We discuss about vibrational spectra or harmonic oscillator model. You can see that infrared radiation in the range of 10 to 1000 to 100 centimeter per centimeter is absorbed and converted by an organic molecule into energy of molecular vibration. This absorption is quantized by the Hooke's law, F equals to minus F into delta R, where small f is the force constant. A simple harmonic oscillator is a mechanical system consisting of a point mass connected to a massless spring. The mass is under action of a restoring force is proportional to the displacement of particle from the equilibrium position and force constant F, also K of the spring. The vibrational energy can be calculated using the classical model of harmonic oscillator at given as VR equals to half K into delta R square equals to 2 pi square into mu V into delta R square, where mu equals to M1 into M2 divided by M1 plus M2. The vibrational frequency is generally increases with increasing the force constant, increasing bond strength, and decreasing mass. The vibrational energy can be calculated using the classical model of harmonic oscillator using the potential energy function in the Schrödinger equation. The vibrational frequency can be calculated at mu equals to 1 by 2 pi root under F by mu. This is the example F equals to Cc triple bond, Cc double bond, and Cc single bond. So you can see here that the force of the triple bond is more as compared to double bond is more equal compared to single bond. Now we talk about the vibrational spectra. A harmonic oscillator model. The actual potential energy of vibration fits the parabolic function fairly well only near the equilibrium internuclear distance. The Morse potential function more closely resembles the potential energy of vibration in a molecule for all internuclear distance and interatomic oscillator model as given delta E equals to the En plus 1 minus En, that's equals to h nu and nu of the oscillation. The energy distance between the transition from n to n plus 1 correspond to the energy of the observed light quantum, and the difference between the two adjacent energy level gets similar with increasing the n until the association of the molecules occurs as a dissociation energy. A weaker transition called overtones are sometimes observed. These correspond to delta nu equals to 2 or 3 and their frequencies are less than 2 or 3 times of the fundamental frequency because of the aharmonicity. Typical energy spacing for vibrational level are on the order of 10 to 20 joule. From the Boltzmann distribution, it can be shown that the room temperature, typically 1% or less of the molecules are in excited state in the absence of external radiation. Thus, the most absorption transition observed at a room temperature are from V0 to nu equals to 1 level as shown here. Now the vibrational spectra 3, because of the rotation vibration transition, the vibrational spectra appears as a bands rather than the lines. When vibrational spectra of gases, diatomic molecules are observed under high resolution condition, each band can be found to contain a large number of closely spaced components. Band gives a spectra in the form of band. The structure observed is due to that a single vibrational energy change is accompanied by the number of rotational energy changes. The form of such vibration rotation spectra can be predicted from the energy level of a vibrating rotating molecule and termed as vibrational rotational band. A vibrational rotational absorption transition from n to n plus 1 gives rise to 3 sets of lines called branches. The lower frequency, that's known as P branch, where the delta nu equals to 1 and delta j equals to 1. Higher frequency is called R branches, where delta nu equals to 1 but delta j equals to plus 1. However, the third branch is the Q branch, where delta nu equals to 1 and delta j equals to 0. Now it talks about the molecular vibration. How many vibrations are possible? That's the question. A molecule has many degrees of freedom as the total degree of freedom of its individual atoms. Each atom has 3 degrees of freedom corresponding to its Cartesian coordinate like x, y and z axis. Thus, for n atoms molecules, there will be 3n degree of freedom. In a molecule's movement of the atom is constrained by interaction through the chemical bond. Now talk about the translation. The movement of the entire molecule while the position of atoms relative to each other remains fixed. So 3 degrees of translational freedom are there. And in the case of rotational transition, interatomic distance remain constant, but the entire molecule rotates with respect to 3 mutually perpendicular to axis, that the 3 rotational freedom and 2 rotational freedom in the linear and 3 rotational freedom in the non-linear. Here we discuss fundamental of the vibration. Vibration are actually relative position of the atom change, while the average position and orientation of molecule remain fixed. For example, we discussed that the bending of vibration are more often subdivided into scissoring, rocking, wagging and twisting. You can see here in a model that how the bending, scissoring occurs, how the rocking occurs, how the wagging out the plane and twisting out of the plane. So for that we can calculate the degree of freedom for the translational vibration. If it is the linear, then 3 degrees of freedom, and if it is a non-linear, again 3 degrees of freedom. For rotational, it is for the linear it is the 2, and for the non-linear there are 3 degrees of freedom. For the linear 3n-5, and for non-linear it is 3n-6. So the total is 3n, and total for the linear, and for the non-linear it is again 3n. There are 2 types of vibrational model. Vibration can either be involved change in bond length or bond angle. If it is change in the bond length, it is called stretching, and if it is change in the bond angle, it is called the bending. And based on that, there are further divided that I discussed already. Now we discuss about the selection rule. The energy associated with the quantum of light may be transferred to the molecule if work can be performed on the molecule in the form of displacement of charge. Selection rule. First, a molecule will absorb IR radiation if the change in vibration state is associated with the change in the dipole moment of the molecule. So the dipole moment equals mu equals to QR, where Q is the electrical charge and R is the distance between that charge. For some defined origin of coordinates, and from the defined of the molecule, the dipole moment is greater when the electronegativity difference between the 2 atoms in a bond is greater. Some electronegativity value was given here. For example, we can ask you that for hydrogen 2.2, for carbon 2.5, for nitrogen it is 3.04, for oxygen 3.44, for fluorine 3.98, and phosphorus 2.198, sulfur 2.58, chlorine 3.16. And vibrations which do not change the dipole moment are infrared inactive compound, that's known as the homonuclear diatomics, because in the homonuclear diatomics there is no difference in the electronegativity. That's what dipole is not generated, and thus you don't get any IR band. Then with this talk we can say the why not 3n-6 into divided by 3n-5 bands in the IR spectrum. The theoretical number of fundamental vibration like the absorption frequency will seldom to be observed. The overtones multiple of the given frequency combination or sum of the 2 other vibration or the difference in the 2 other vibration tones increases the number of bands. So the following effects will reduce the number of theoretical bands, like the frequency which falls outside the measured spectral region for in between 400 to 4000 wave number per centimeter, bands which are too weak, bands which are too close, and occurrence of degenerate band from the several absorption of the same frequency, and the lack of change of molecular dipole. We discuss about the IR spectrum. Whenever you take the IR spectrum of any of the sample, either it is a protein, DNA, organic compounds, inorganic compound, it will give you a typical IR spectrum. But the knowledge of IR spectrum is essentially important because you should understand what information is hidden in the spectrum. So for that, you first know the group frequency. With certain functional or a structural group, it has been found that their vibrational frequency are nearly independent of the rest of the molecule group frequency. For example, carbonyl group having 650 to 740 per centimeter, and various as for the various aldehyde and ketones. For many groups involving only one atom, the approximate frequency of the fundamental vibration can be calculated from a simple harmonic oscillator model. Calculations show that most group of interest characteristic frequency of a stretching vibration should be lie in the region of 4000 to 1000 per centimeter. In practical, the region from 4000 to 1300 per centimeter is often called the group frequency region. The presence of various group vibration in the IR spectrum is of great assistance in identifying the absorbing molecule. In this figure, we show a typical IR spectrum, which is divided into the 4 distinct regions. And the plot is actually x-axis. We plot the value of frequency or in the form of wave number, and in the y-axis it is either transmittance or absorbance. Both, any one can be taken. Only the difference is that if you take the transmittant, the spectrum are inverted. However, if you take the absorbance, the spectrum are upright. You can see here from the extreme right side, this region 4 is called, give you the information about the stretching, bending, combination of band, and that is known as fingerprint region. So most of the atoms, most of the molecules can easily be identified by taking its fingerprint spectra in the fingerprint region. You can see that most of the organic compound having a typical region in the fingerprint spectrum. However, the second region is giving the information about stretching in carbon-carbon double bond, carbon-oxygen double bond, carbon-nitrogen double bond, and bending of nitrogen and hydrogen bond. In the third region, this lies around in the region of 2000 wave number, and it having the gives you the information about carbon-carbon triple bond, carbon-nitrogen triple bond, and XYZ stretching. And the first region, it is the region of highest frequency, give you the information about the single bond stretching between OH, NH, and CH stretching. But it is very important to note that if you get the spectra of fingerprinting region, you can easily identify any molecule of the interest very easily. However, these information like the CO and the double bond and triple bond and if you further help you to confirm your identification. And nowadays the IR spectrum of the most of the compound are available in the website. You can compare your spectra and you can easily identify as well. We give you detailed information about the different types of bonds present in different types of compound and what is its frequency range. So that help you to identify any signature if you collect from the IR spectra. For example, you can see the CH single bond of the alkane gives a very strong absorption intensity in the range of 2850 to 2970 and 1340 to 1470. However, CH in the alkene, that's the conjugated with the double bond, gives you a medium intensity in the 3010 to 3095 and a strong intensity in the 675 to 995. But the same CH bond, if it is associated with the triple bond in the case of alkyne, it will give you a strong intensity peak at the frequency of 3300. And the same CH bond, if it is associated with the aromatic ring, it will give you a medium peak in the frequency range of 3010 to 3100, and a strong peak at the 690 to 900. And if you take the other bond like the OH, again if it is associated with the monomeric alcohol like primary alcohol, then the hydrogen bonded alcohol with phenol, monomeric carboxylic acid, and if OH is hydrogen bond with the carboxylic acid, it is showing a variable intensity in the different region. For example, in the monomeric alcohol, in phenols it gives 3590 to 3650, and hydrogen bonded phenol is giving 3200 to 3600. Similarly, monomeric carboxylic acid give you 3500 to 3650, and hydrogen bonded carboxylic acid give you 2500 to 2700 broad peak. Now we discussed that what are the different typical signature for the amines, like it is the NH bond, you give a medium intensity in the 3300 to 3500. For the alkene, carbon-carbon double bond, 1610 to 1680 with a variable intensity. Aromatic ring, carbon-carbon double bond give you 1500 to 1600 variable peak. Alkyne gives you the variable peak at 2100 to 20260. And for the amide, you get a strong peak in the range of 1180 to 1360. And for the nitrile, that the carbon nitrogen triple bond cyanide group, you get the strong peak at 2210 to 2280. For the CO bond in the alcohol, ether, carboxylic acid and ester, you get a strong peak at 1050 to 1300. And CO double bond in the aldehyde, ketone, carboxylic acid and ester, a strong peak at the 1690 to 1760. And for the nitro compounds, you get a strong peak at the 1500 to 1570 and 1300 to 1370. Now we can say that the fingerprint region is the most important component of the IR spectrum, because in this region is lies from 1300 to 400 per centimeter. Vibrational frequencies are affected by the entire molecule, as the broader range of the group absorption in the absorption shown as a fingerprint region. Absorption in this fingerprint region is characteristic of molecule as a whole, and this region finds widespread use for the identification purpose and comparison of the library of the spectra. Now we talk about the main application of IR spectroscopy. It is a widely used technique having lot of application, but here we discuss some important application in brief. First, in the fundamental chemistry, like the determination of molecular structure geometry, determination of bond length, determination of bond angles in gaseous molecule, the IR spectroscopy is most extensively used. Not only this, it is used for the quantitative analysis. For example, having a simple, fast, non-destructive monitoring of trace gases, and rapid simultaneous analysis of GC, moisture of nitrogen in soil, analysis of fragment left in the scene of crime for the determination of hydrocarbon on the filter in air, and many more. It is also used to studying the progress of the reaction. Progress of the chemical reaction can be determined by examining a small portion of the reaction mixture. From time to time, you can see the appearance of bands for the product or intermediate, and disappearance of the bands for the fingerprint bands for the reactants give you the kinetics of the reaction as well, and the formation of the deformation of reactant and products as well. It is also used for the detection of impurities, like it can for a test sample can be compared with the standard compound, and you can find out what are the impurities present in any kind of sample. So students, now let's summarize what we have learned in this module. The IR deals with the interaction of infrared radiation with the matter, and the IR spectrum of a compound can provide important information about the chemical nature and molecular structure. Most commonly, the spectrum is obtained by measuring the absorption of IR radiation, although IR emission and reflection are also used. It is widely applied in the analysis of organic, inorganic, and organometallic compounds. The absorption intensity depends on how efficiently the energy of electromagnetic wave of frequency can be transferred from atoms involved in the vibration. And the infrared region is further divided into three sections, like the near IR region, mid IR region, and far IR region. And of course, greater the dipole, more intense the absorption occurs, and greater the molar extinction coefficient, like the Beer-Lambert law, it also gives you the more intense IR peaks. So IR identifies the component of sample in all the forms, either liquid, solid, and gases, and absorption of IR is restricted to the compounds with a small energy difference in the possible vibrational and rotational states. For a molecule to absorb IR, the vibration or rotation within the molecule must cause a net change in the dipole moment of the molecule. The IR spectrometer measures the interaction of IR radiation with the molecule. Intensity and frequency of the sample absorption are depicted in a two-dimensional plot called IR spectrum, and intensity is generally reported in terms of absorbance and the amount of light absorbed by the sample, or percent transmittance, that is the amount of light which passes through it. And what makes up an unknown sample and how much each component is present in that sample can have valuable information supplied by this technique. It have many applications in the research and development and the new products from the chemistry, biology, medical science, clinical science, in all the field of science. It is used as a most widely used technique for the different purposes. So I hope you understand a detailed information on the IR spectroscopy. Thank you very much.